Hi everyone, and welcome to this short video, hopefully short-ish, which is just going to take you through a bit of a refresher on one of the key concepts from the biological approach, which is going to be neuroanatomy. So please get your booklets out and open in front of you to page 57. Obviously, some of you might have filled this in using the PowerPoint that you were provided with. Some of you might have been a bit overwhelmed with it and not got this far. Either category is absolutely fine, okay, as long as we've all got this filled in now, okay? So open to page 57, highlighter pens at the ready. The key concept that this video is going to guide you through is neuroanatomy. So to define neuroanatomy, it refers to the structure, if you can highlight that word for me please, of the brain and also the nervous system, which we're going to look at in more detail next week in the lessons. And there are a series of different things that you need to know about concerning neuroanatomy, including localization of function, lateralized function, and brain plasticity, all of which you came across a little bit in the SIL, okay, I believe. So we're going to start with localization of function. Again, if you want to update or amend what you've already written in on page 57, that's fine. But when we talk about localization of function, this is simply the idea that certain functions, for example, language and memory, are thought to be located within certain areas of the brain. So if I use the word localized, I'm talking about a specific area or a specific behavior. So localized function, the idea that certain functions reside or are found in certain locations of areas of the brain. Now, the first case that demonstrated this possibility of localized function to us was Phineas Gage. So I don't need to refresh the details of what happened to him. I think you're all quite familiar with this case by now. But what you do need to know for the biological approach is what this case shows us about localization of function. So it shows us three things. Again, if you've taken notes from the PowerPoint already, you might want to update this, okay, and add on a couple of extra bits. So three things. First thing is it demonstrates that, that's a typo, demonstrates that localized damage to the brain results in very specific behavior changes. So we now know, all right, that wherever the brain damage occurs, we can expect a very specific or niche set of behavior changes to occur. So that's number one, okay? Second thing that the case of Phineas Gage demonstrates to us is that the frontal lobe was the region that he damaged, and behaviours that changed, therefore, are subsequently or since then referred to as localised to the frontal lobe, okay? So because it was specifically his frontal lobe, that little yellow part of the brain on the image, on that the bottom image, because it was his frontal lobe that was damaged, and because it was a very specific set of behaviour changes that occurred, we now believe those behaviours to be localised to the frontal lobe. And those behaviours include the following. We now think that the frontal lobe is involved in decision making, because Phineas Gage couldn't make rational decisions anymore. It's involved in logical and rational thought. He was impulsive, he was hot-headed, he couldn't be logical, he was just angry all the time, and he got really agitated really easily. There was no kind of rationality to him at all. And obviously it's involved in some, not all, but some regulation of mood and anger. So that case was one of the first cases to demonstrate localization of function. And since then, alongside the development of kind of technology, into the 21st century, we now have a much better understanding of localized regions of the brain and the functions that they house. So we now refer to, bottom of page 58, the different cortices of the brain. And we know that specific damage to these specific regions will result in specific behaviour changes. So the four regions that you need to be familiar with are, you can see on the screen, the motor cortex, the somatosensory cortex, the auditory cortex, and the visual cortex. They're grey on your booklet, so it might be an idea to just get a highlighter or a coloured pen and just make them stand out. But the motor cortex is that initial pink slither of cortex that runs down the back of what we call the frontal lobe. The end of the frontal lobe is the line between the pink and the green slither on this screen. So the motor cortex sits at the very back of the frontal lobe. The somatosensory cortex, which is the green ridge, is part of what we call the parietal lobe, which is the kind of top region of your brain going down to the base of the brain. Okay, so parietal is kind of the top and bit of the back of the brain. Moving down in a clockwise direction, we then hit what we call the occipital lobe, which contains the visual cortex. So the visual cortex is the very back region of your brain. So if you've ever heard the term eyes in the back of your head, that's where that comes from, because everything visual is processed right in the very back region of your brain. And the auditory cortex, again following it round in a clockwise formation, is the very kind of centre of your brain. So obviously localised to where your ears are, that's where all your sound systems are. So we call that the auditory cortex. So obviously, for the purposes of the exam, you not only need to know and be able to label those regions of the brain, you need to know what happens to them if we experience damage in those areas. So the motor cortex is basically all to do with movement in the body, okay? But please just highlight for me that each hemisphere has an area which controls movement on the opposite side of the body. So your left arm is essentially controlled by your right hemisphere and vice versa, okay? So all the bits of your brain that tell your right arm to move are all located on the left side of your brain. Doesn't make much sense, okay? It's what we call contralateral communication, but just make that stand out for me. So if we damage our motor cortex, you're probably going to experience some problems with what we call fine motor movements, such as tying your shoelaces, holding a pen, holding a knife and fork, etc. Somatosensory cortex is, we saw, kind of lying adjacent to the motor cortex, okay, so it runs in parallel. It runs across both hemispheres of your brain, so it's a slip that goes, or a strip rather, that goes right across the top of your brain, and this deals with sensory information. And it's interesting as well to note, if you want to highlight this, that the sensitivity of an area of the body corresponds to how much cortex or grey matter exists within that region. So your hands, your face, your genitalia are some of the most sensitive regions of your body, and that's because they make up almost half of that strip of your brain across the centre. So when we're experiencing kind of sensations in our hands and our face and other sensitive areas of the brain, it's because we've got so much cortex designated to those parts of our body. And if you were to damage the somatosensory cortex, you'll experience numbness and tingling in whichever part of your brain that you have damaged. So if it's the bit that corresponds to your face, then you'll get a tingling sensation somewhere on your face. The visual and the auditory cortex are pretty self-explanatory. Visual cortex, like I say, at the very back of the brain in what we call the occipital lobe, processes all visual information. So if you were to damage that, then you'd probably experience some sort of partial blindness or some sort of problem with processing visual information, shapes, colours, etc. Auditory cortex processes all sound and spoken language, so if you experience damage to that region, probably going to be some sort of partial deafness or maybe problems with interpreting speech and language we tend to find as well with the auditory cortex. So they are your cortices, so you need to try and learn the different cortices, be able to label them and also know what happens when we damage them. So moving on to the next little bit of neuroanatomy, an entirely separate set of ideas to localized function is now lateralized function, which is the idea that certain functions are controlled by one hemisphere and they only exist on one hemisphere rather than the other. So according to neuroscientists, the brain and its functions are split across the right and the left hemispheres. Hemisphere, guys, is just another word for half, okay? So all functionality is split between the right and the left halves or hemispheres of your brain. So let's find out what exists on these different hemispheres. Just to clarify as well, remember I've said that the right side of your brain processes left visual information and vice versa, okay? So don't get confused with that. So we're going to start with the left-hand side. So based on what I've just said, the left brain controls your right hand and your right arm ability, for example. It also houses kind of classic academic skills, I would say. So people who are left-brained are often more inclined or more drawn to kind of pure academic subjects such as maths and science. They tend to have good mathematical and scientific abilities. They also tend to have quite good language abilities, both spoken and written, and they tend to be really quite logical thinkers, okay? So they can work through problems and resolve problems quite easily, okay? So we've got maths, science, spoken language, written language, and a lot of logical thinking. On the right hemisphere, so if you're right-brained, you tend to be viewed as a bit more creative. So in the right brain, we would classically find imagination centres, appreciation of art and music, recognition of three-dimensional form, which is shape and colour, so which is obviously important for art awareness. But these people tend to have quite good levels of insight as well, so they understand people and they're creative thinkers, for example. So again, try to learn some of those things that belong on the different hemispheres. You can either write them in on page 59 or fill in the spaces on page 60. And I have included as well for you the link that's included on page 60 in your booklets to see if you can find out whether or not you are a right or a left brainer. So then the final concept that we just need to have a look at in relation to neuroanatomy is plasticity. So I've already filled this in for you, so go ahead and get these popped in. Plasticity, in my opinion, is the brain's kind of most miraculous capability. So plasticity refers to the brain's ability to change and adapt in response to new experiences or just simply new learning. So your brain is not a fixed structure, it's constantly changing. You lot are just doing your A-levels and BTEC applied courses, so you're constantly learning. That means that right now your brain is changing. New neural connections are forming in your brain to allow you to understand the material that you're being taught by your teachers. So that's what we mean by plasticity. Your brain's ability to change due to new learning or new experiences. Now, the changes in your brain, weirdly, can be both structural, if you want to highlight that, where your brain physically changes when you learn something new, or it can be functional, whereby if you've unfortunately experienced some sort of illness or injury and you've got a damaged region of your brain, then undamaged or healthy regions of the brain can actually take over the functions of the damaged areas. So for example, if you want to pop this in your booklets, there's a very famous case of a little girl who was 8 years old when she had one full half of her brain removed, so her left hemisphere was entirely removed. And after about 2 months, I think it was, she'd fully recovered every single function from her left hemisphere into her right hemisphere. So that's what we call functional recovery, where a different region of your brain can pick up any damaged areas or lost functions of the other region. Now, we also tend to say that plasticity is at its very highest peak in young infants who are typically under the age of around about 2. And we need to try and explain why and pop this into our booklet. So we normally say that this is because they are constantly learning. So every new experience is creating a change. They've got to change their brains to be able to accommodate for those new learning experiences. For you guys at around about 16, you've still got a healthy rate of plasticity, so you're still forming, quite a lot of new pathways, but you are depleting and deleting some neurons as well. Unfortunately for me though, at nearly the age of 40, my neurons are on the decline, okay? So I've probably got less than 50% of the neurons that my 2-year-old has got, okay? So your brain goes into decline once you get past that peak of new learned experiences. So that's plasticity. And the only other thing that we need to go through together in this video is just a classic study which is used to illustrate plasticity. So you don't have to scan that QR code, you can if you want to. It takes you to a little video clip. Instead, apologies about that, if you want to just copy some of the details down about this study, which does really do a good job of demonstrating brain plasticity. So the aim of Eleanor Maguire's study was to examine whether or not structural changes occur in the brains of people who have experience of spatial navigation. So the people that she selected to participate were taxi drivers. Because of the spatial demands that are placed onto these people, we tend to see that they've got really good kind of spatial capabilities. So she wanted to see whether their brains looked any different. So what she did was what we call a structural MRI, okay, with 16 male taxi drivers. She then compared their brains to the scans of 50 healthy right-handed males who didn't drive taxi drivers. All the males who were taxi drivers, so all 16 of them, had been driving a taxi for at least 1.5 years. The results showed that in the taxi drivers, there was increased grey matter, okay? So increased grey matter, i.e. more brain, more cells, was found in the brains of the taxi drivers compared with those who were the control in 2 specific regions, and these were what we call the right and the left hippocampi. Now the hippocampi we know is involved in spatial memory, but what we're saying here is those people who were taxi drivers had a bigger hippocampus. Also, it was the back of their hippocampus which was bigger or had increased volume, because that's the one that deals with more kind of direction capabilities. And what they also found, if you want to write down, is that the longer they'd been a taxi driver, the bigger their hippocampus got. So not only did they have bigger hippocampi compared to non-taxi drivers, those who had been driving taxis for 10, 15, 20 years plus, they had the largest hippocampus. So their brain had continued to change to accommodate for that new learning gradually over time. And they had a far bigger grey matter in the hippocampi region than those who were not taxi drivers. So hopefully that study demonstrates to you the very nature of plasticity and that your brain can continue to change throughout your lifetime. So that's the refresher, guys, on neuroanatomy. You do have a couple of other little things to do for me just to prepare you for the lessons next week. So I've given you some PowerPoint slides to just refresh the key assumptions, and I've also given you a sheet that you need to print out on neurochemistry. So print that out and complete that and bring that to lesson, and then hopefully we'll be able to get through the biological approach no problems next week. Hope that's helped, guys. Okay, thank you.